Hi, everybody, and welcome to today's webinar, Advanced Memory Architectures to Overcome Bandwidth Bottlenecks for the Exascale Era of Computing. I'm Addison Snell with Intersect360 Research, and I'm going to be the moderator for today's panel. And wow, what a very topical topic that we're going after today. And this is really right on point. And I'm excited not only about the content that we've got for today, but also the panelists that we have joining me. And I'm going to introduce everybody just quickly here, starting with Mohammed El-Battal, who's the Chief Technologist for Cloud Systems at Seagate Technology. Mohammed, thanks for being on the panel. Ivy Peng, computer scientist at Lawrence Livermore National Laboratory. Hi, Ivy. Bill Magro, chief technologist, high performance computing at Google. How's it going, Bill?
Good. Thanks for having me, Addison.
Vladimir Stoyanovich, co-founder and chief architect at Ayar Labs. Vladimir, great to talk to you today.
Hello.
And Martin Terpstra, Senior Director of PLM and Business Development, High Performance Networking and Silicon Photonics at HPE. Martin, thanks for being on the panel.
Thanks for having me.
Before we get to the content, I'm going to start with a couple of housekeeping notes for our attendees. We are going to have live audience Q&A at the end of this session. Now, this is, in truth, a pre-recorded portion here, and our panelists are monitoring the chat as it goes by through this pre-recorded portion. So you can interact with our panelists on the chat function or submit questions through the Q&A function. And through the magic of modern webinars, we will be back to take them live at the end of this panel. Before we dive into all of the questions, I've got a few notes as the industry analyst just to set context. We're here at the dawn of the exascale era, and one of the main challenges in building systems of that scale has been networking, particularly in terms of how we connect a far-flung aggregation of processing elements to each other and to data in memory so that they can work in parallel at scale. There's that notion of the last mile is memory, right? And tremendous work has already been done here. And I don't mean to diminish any of that, but the hope, of course, is that we can continue to make progress in networking, not only for the complete apex of supercomputing, which we're talking about with Exascale, but for the broader high performance computing market. And here's where it gets interesting, because Intersect360 Research has recently completed a new comprehensive survey of software environments in high performance computing. And we found that across all applications with over 2,000 data points, typical HPC job scalability is 4 nodes or fewer for about half of all HPC applications and 16 nodes or fewer for 75% of all applications. It does not get much better that's typical job scalability. If we talk about maximum job scalability, it doesn't get much better. 56% of all total applications at 16 nodes or fewer for maximum scalability, and less than 15% going over 128 nodes for maximum scalability. Now, this raises the question as to what's getting in the way of that scalability. And to what extent is networking and memory access an issue? Furthermore, we've been tracking configured memory as part of systems. And what we found is that over time, configured memory per core going into new systems has stayed relatively constant. It's actually gone up slightly, continues to go up slightly. And as we've looked at changes in computing architecture, we've been having more cores per socket, even a slight increase in sockets per node. You keep memory per core constant or even increase it a little bit, the amount of memory going into these systems keeps going up, which brings up the question of efficiency. Now, Ivy, I'm going to come to you first because Lawrence Livermore National Laboratory has done some research of its own regarding HPC applications and memory access. What did you find, and is that consistent with what we're talking about from the analyst side?
So in general, we are continuing to explore how workloads requirements evolve and how to cope with their requirements for larger or smaller simulation capacity. So as I shown here in this slide is how we conduct a survey on an open-end supercomputer. we do find some results are slightly different for closed-end supercomputer. So what we're showing here is basically a overall memory utilization as shown in the node hour, which is consistent with some other studies that 75% of the time, a node will use less than 23% of memory capacity. So this is a general takeaway. How are we going to keep scaling up memory capacity over or beyond the exascale, or are we looking for other alternatives? But a more interesting finding is actually we found how the memory intensity changed in the past 3 years. That's why we're showing the shift in the red bars here, how they are shifting towards the right-hand side. They are actually increasing in the node capacity. And a more dramatic change is in this kind of yellow bars. Those are those memory intensive workloads. They have very dramatic or doubled memory capacity requirements in the past 3 years. So the takeaway is there's very rapid change in the workloads on the same system over time. And how could we kind of cope with that? Obviously, we do not build a machine that often, so we need to find a better way to provide that resource.
It's excellent setup for what we're talking about here with advanced memory architectures and how they apply to bandwidth bottlenecks, which really brings up the first major question: how do we view memory bandwidth and these bottlenecks today as they apply to HPC systems and applications today? Martin, I'd like to come to you first on that. You know, you've heard this industry setup. What's your view on that topic?
It's interesting, right? Because if we look at, resource sharing, resource pooling, right? It's not a new concept. It's been around for quite a while. But what we're finding in some of these high-end applications, and obviously memory is the place where we're talking about it here, but it has taken us a while to get to a point where we can effectively pool memory in a way that it is as performant as it would be as it's local, right? And we're sort of approaching that point in time of both technology, maturity of control systems and everything else, that we can actually get to a point where we don't necessarily have to have memory right next to us, right? Like the data points show, we've been solving this problem typically by simply adding more memory close to where the compute is. We're getting to this point where networking technology, and I'm using networking sort of broadly, like I think you are, because it also becomes sort of a system interconnect, and then the lines are blurring between what typically was a network and as a system interconnect. The technology is coming to a point where we can actually increase the distance between where you do your compute and where your memory is without taking a significant penalty for performance. And I think that's exactly the goal of trying to get to a better utilization of a distributed shared memory system.
Yeah, it's a great point. You caught me being lazy with my terminology, which as an analyst, I shouldn't be, because if we're talking about network or interconnect, but really at this level of scale, we're getting to where we can view memory as a peripheral device. So as we talk about memory bandwidth, that's a form of networking, and how we connect these elements becomes really important at scale, because the larger the system is, the less convenient it is to have all the memory close to all of the processors. So I appreciate you bringing that up. Vladimir, what do you think about this topic?
This is indeed a really challenging area. And I think some of your earlier comments were made about the kind of the strong versus weak scalability of the systems. I think has a lot to do with kind of the root cause being that networks have been kept being networks. And what we really need to enable the scalability of these systems is a lot of work on memory semantic fabrics, or turning these networks into something that can carry the memory transactions really well and allow us to scale kind of beyond the chassis level. Like a lot of these numbers of the strong scaling that you mentioned earlier were really chassis level scalability numbers of how many nodes you can, or sockets you can put and call it a node essentially in a chassis. And the reason for that is simple. At the end of the chassis, there is a network interface, and that network interface has somewhere between 10 and 20x lower bandwidth than what let's say we would call a system interface or interconnect within the chassis. And we need to overcome these problems to be able to allow the sockets to more broadly address these physical boundaries or transcend them. in Ayar Labs, we've been working on optical I/O that does exactly that. Directly from the socket gives you tens of terabits per second, pretty large system fanouts, so that you can not only establish pipes to a lot of other processing units, but also to memory modules, but also with fine granularity, so that you can support the fanout that's necessary in these applications.
Yeah, I love that. When you talk about the memory wall, and sometimes it's only metaphorical, but you get to the end of the chassis and there's sort of a literal wall there. From one rack to the next, there's a piece of sheet metal that can become a memory wall of a literal sort. Now, Mohammed and Bill, I saved you for the end because you both got a little more of a cloud perspective in addition to an HPC perspective. And cloud, talking about whole new realms of scalability. So I wanted to put you next to each other here, Mohammed.
Sure.
What do you think about this?
Yeah, the memory wall, I guess, as you mentioned it here, it's interesting because a rack level scale, even for memory interfaces and sharing memory on a temporal basis between CPUs that are executing on specific applications on a memory pool, as we view it today, is a challenge, and we're addressing that challenge. We're identifying the latency issues that we're having to deal with, the bandwidth issues that we're having to deal with. Obviously, applications are more memory hungry today than they were, and they're more memory bandwidth, as well as latency hungry. So, the CPUs have scaled almost 100x, in the last 12 years. And if you look at memory, it has a quarter that level of scaling, as well as the bandwidth is almost an order of magnitude lower in terms of scaling and capability and latency scaling. So, the challenge is to find the right interfaces, the optical solutions that are going to bring those private fabrics within the rack to interconnect the solution and provide a pool of shared memory resources that can be utilized and on a temporal basis, switch from one application to another, or from one orchestration layer to another. And really the difficulty is going to become in multiple layers: the OS layers, the orchestration APIs, and the connectivity of the optics and the various solutions, and how to tie everything together in a composable, disaggregated solution. Bill?
I'm glad you brought up latency, and we're going to come back around to that, but I do want Bill to get in there first. Go ahead, Bill.
Yeah, I guess first I just take a kind of a workload perspective. So, as Mohammed said, the memory wall. If you look at HPC workloads, they tend to be at any point in time, memory bandwidth bound or compute bound. A lot of times we try to put them in simple buckets, but the reality is most workloads actually go through phases. And one of the challenges, I think, comes from it's just that we live in a three-dimensional world, right? So as we grow the chips and the process becomes more dense, the compute power is growing, as the square, right? The area, and you get the process advances, but the perimeter of that chip is only getting big linearly, right? And what it means is the ratio of what you can do in compute versus basically how many wires you can put on the perimeter of a chip to get that I/O bandwidth. When you combine it with the limitations of how fast you can wiggle a signal on a copper wire, it's just physics and geometry here has driven us to where we are. And if you plot the memory bandwidth from 20 years ago on the supercomputers to where we are today with microprocessor-based systems, it's clear we're moving into an area of effectively, a lot of inefficiency for any of those workloads that are doing sparse accesses, whether it's all the time or just intermittently. And especially around the way cache architectures put a big load on a memory subsystem, even when you're only using a small amount of the data and you're jumping around, maybe pointer chasing and so on. So we talked about the scalability of workloads and really didn't make the tie back to memory bandwidth. But the reason people don't scale their workloads is oftentimes they've got a code that's licensed, for example. And so it's a cost optimization, not a performance optimization. Maybe it would go 10% faster if you added 20% more cores, but it gets more expensive to complete that job. And when you have lots of jobs to complete, it's more efficient to push those through rather than run a single workload faster. So there is actually a connection between the challenges and the efficiency we're running into as we run out of memory bandwidth back to the scale which people do their computing.
I love that we hit all of these topics on our first round robin. I heard about disaggregated architectures. We heard about latency. We heard about the limitations of copper, and that's going to be a great jumping off point. Before it becomes more of a free for all, I want to loop around back to Ivy. You've heard sort of everyone else talk about their view from an architecture standpoint. You're at a national laboratory at that apex of scalability. How do you see this challenge? And in particular, you talked about the amount of memory coming in to these nodes. Is that in a sense over provisioning in order to get around some of these memory bandwidth and latency issues?
I think one of the requirements of the lab, the facility would like to provide support a large range of simulations, which is very diverse characteristics. So one thing I could share here is how accelerator-based workloads will have different requirements compared to CPU-based the workloads, and they have very different memory hotspots here. And this is something that we should consider how in the future, when more heterogeneous system with different accelerators coming into the system, they would kind of complicate the memory requirements, especially in bandwidth. For instance, the GPU workload, they want just fit into the HBM memory, right? So if we look at how the workflows, this kind of emerging like complex workflows of different components is kind of combining HPC, AI, or data analytics components together to work. They kind of have different phases. And different components also have a different requirement on the bandwidth or latency based on what they are actually doing. So what we're showing here is how these kind of diverse requirements could cause a kind of temporal imbalance in memory requirements, and how they could have very different utilization on different groups of nodes that are assigned to different components. So all these are kind of considered together with how quickly we see that the workloads on the same machine could kind of adapt over the time. This is something we find interesting, and of course, with more understanding of the workloads, that will definitely help to explore different solutions.
Yeah, you bring up yet another compounding factor, which is we're increasingly talking about heterogeneous architectures. Over 90% of HPC users have accelerators configured somewhere as part of their HPC environment. So now you've got another type of processing element that's not on the main memory bus and might be connected through PCIe or some other sort of interconnect. Now I'm going to kind of open it up about how does that make things even more complicated, and what other considerations do you have for accessing memory at scale in these heterogeneous environments?
One of the points that I was going to bring up was, and as a system vendor in trying to construct HPC, and almost, I don't want to narrowly focus on HPC, because I think there's sort of a path into AI with a lot of this stuff as well.
Sure.
But what we're finding is, what we've done traditionally is, you look at a customer, you look at the type of workloads they intend to run, and you try and sort of design a system that is optimized for those kind of workloads, right? And what we're finding is, in the past, there were many applications where you could do that, right? You could design a system that was fairly well tuned to the type of workloads. But more often, right, and you saw it, right? You said it in the beginning with some of the smaller workloads in the middle, the diversity of workloads is going up tremendously, right? Which means that how do you build a system, right, that can be well performing for all kinds of different workloads that you cannot tune? And as a system provider, like, we'd like to make sure that we can actually build a system where you can mix and match as best you can without adding additional costs. And I think this is one of those places. This is going to be economics driven, right? How do you build and use systems that are heterogeneous, but not built to support one specific workload or one specific utilization form factor?
Excellent points. Anyone want to jump on that?
Yeah, I'll just add something there, which is, we talked about the limitations of copper and the length, right? The longer the wires get, the harder it is to drive, a good signal and high speed. And with the limit around the perimeter around the chip, people are moving to 3D stacking, right, as a way to explore that third dimension. They're bringing HBM into the packages. We've seen this in the GPU world for a long time. We're starting to see it happening in the CPU world. But as soon as you do that, you're, to Martin's point, as the diversity of workloads goes up, what you've done is you've driven heterogeneity effectively into each chip, but you still have a challenge with homogeneity across your system, right? Trying to meet the needs of particular workloads that scale the farthest, right? They need a lot of homogeneity at the system level. And then as you move this diverse workload mix through, either whole workloads or in a mix of them, you end up with resources getting stranded, right? Because you've made a fixed ratio of, say, HBM quantity to cores or whatever your metric of choice is. And so there's an inefficiency that comes as a result of optimizing, to deal with the physical problem. So we really get pushed into a pretty difficult corner when we're limited to working with short copper wires.
Yeah, this type of diversity in applications really has come up in our research as well. And it's been kind of obvious. I mean, 10 years ago, we were all talking about big data. And if you went to the SC conference, it became a big data show. And all of a sudden we had to do analytics. HPC was dead. We were only going to talk about big data. And then that we kind of went past that. And now the new wave has been machine learning and artificial intelligence. And so now we find that over 80% of HPC users already have machine learning as part of the HPC environment or are now working to incorporate it. I've got to do my analytics. I've got to do my machine learning, and my previous scientific workloads didn't go anywhere. I've still got to do those. Nobody tripled my budget. And that's led us back to this notion of over provisioning, where it seems like on each node, I've got to put a maximum amount of memory or maximum number of GPUs that I might need on that node. And that's really set up this discussion of, Mohammed mentioned, new disaggregated architectures that can pool accelerators or pool memory, or this really brought back the term composability, which was the thing more than a decade ago. We were talking about composable architectures, and now I feel like they're getting hot again. How does this panel feel about the notion of disaggregated or composable architectures for the broad range of applications across HPC, analytics, and machine learning?
Yeah, I'll take a stab at this. From a disaggregated solution, obviously the composability piece is something that's not novel to the HPC world, but within a disaggregated solution, to compose resources efficiently becomes a matter of excelling at the tiering layers of what type of composable devices you have, and to allow for the intelligent users to, based on their rack level machine that they're trying to optimize for the workload that they're doing. It's the ability to configure a certain amount of specific latency and bandwidth capable memory that whether it's persistent or non-persistent, and combine it with commodity driven modules that are compute modules or acceleration modules, without over provisioning those from a local memory capability, and try to optimize the layers just like we do with L1, L2, L3 caches, and potentially throw in HBM memory on certain applications where you need to. But in some cases it is viewed as another tier of low latency memory with optical connectivity and emerging memory interfaces like CXL, to bring some of that coherent or non-coherent memory extensions in terms of pools that can be shared between the accelerators that are working on the same data set as the CPU, and you basically have a whole new ecosystem of virtualization of those layers, and trying to optimize the application for the right TCO level from a cloud system, because you really can't predict the workload du jour, but you create a system that can be composed and optimized for the specific orchestration layer that the software that providing all the guiding rails for for the configuration of the system. But again, private fabrics, high bandwidth, low latency, some level of coherency, compatibility. The old non-coherent PCI, failed to do the work in the past. So now we have an opportunity with emerging memory interfaces to do the better job this time.
I love that. And I want to follow up on some of those there's that latency word again. I'm going to come back around on that. But first, Vladimir's been quiet for a little bit. And I wondered if he had a comment on pooling resources and composability.
Well, yes, absolutely. And I think a lot of the previous comments resonate here. If you look at kind of from the physical standpoint, the main limitation to this composability and really being able to orchestrate a system like that is just the severe trade-offs you need to make in bandwidth, latency, and even power in certain cases to access some of these resources in traditional systems. Like if you had a situation where from the compute socket, you could essentially send as much bandwidth to places where you wanted as the chip can generate, like Bill was talking about, you have a totally different view of the system. Of course, also not having to pay an additional latency penalty, right? So you have kind of multiple different boundaries. The first one being how much data can the chip produce? Well, we look at big SoCs nowadays, and
quite a lot, it turns out. Right?
Actually, yeah, exactly. With appropriate on package interface, you can look at HBM3 coming up, right? You will be able to produce 50, maybe 100 terabits per second of data in certain applications, but that only goes a few millimeters. Then you hit the package. The package has package scaling we haven't talked about much, but has been really atrocious compared to all these other scalings that we've seen in the density of HBM memory, in the SoC scaling. And that is a further limit that you need to overcome to both go to DDR5 like CPUs have to go, or if you want to scale out through PCIe and create like a private fabric in a chassis, right? With optical I/O being inside the package, you essentially remove these barriers, and really you get back to this fundamental barrier of like how much can SoC get out. And it turns out, compared to whatever PCIe style fabrics and kind of chassis based links can do today in these systems, the difference between that and what the chip can spit out is even today about 20x, right? So with optical I/O in the package, you would be getting that additional bandwidth boost and the fan out. So it's not only about the bandwidth and how fat the pipe is, but it's how many places you can reach to be able to establish this composability of the system, so that the architect doesn't have to worry, is my memory module in the chassis private next to the processor, or is it somewhere on the shelf in the rack or a few racks below? So I think that's one of the key things that frees us up to think about these composable systems.
Bill, I saw you nodding along there. Did you have a comment, or did you just want to agree with everything that everyone was saying?
Well, no, and the comments are certainly resonating, but I guess one thing I would be interested in saying is that, when you start at a very small scale, if you had, say, I'm just going to think in terms of limits here. This is how they train us as physicists, right? Think in terms of limits. If you just had a single workload and a single node, you could optimize it, to Martin's point. But as soon as you start to bring in that diversity of workloads, you're now designing for the max, right? Which means that at any point in time, except when that one workload that drove the max, and hopefully in every single resource dimension, you have stranded resources, you have waste, you have inefficiency. But as soon as you have that degree of freedom to say, build 100 nodes, you start to get, you could put some diversity into the infrastructure and start to re-optimize, right? By matching workloads with the infrastructure. But it's very difficult to predict that mix. So one of the things that I think is appealing about cloud for folks is that the extreme scale allows the cloud providers to provide more diversity and also start to work with the laws of large numbers. From an ideal perspective, what we'd love to be able to do is say, what's the total compute that's in use? This could apply in a cloud or in a private data center. What's the total memory that's in use? What's the total of any resource that's in use, accelerators, and then just have them in huge pools, right? Just watch the steady state, keep some headroom, and increase as you go. But the reality is, again, physics kicks in, latency. And ultimately, it's the speed of light, right, that's going to limit us. As the compute infrastructure, the compute capability gets denser and denser and goes up and up and up, that latency to memory matters more and more. So I think the interesting
Is
thing
anyone working on improving the speed of light? I thought I heard something in a lab. This is a really old standard that we could probably update, like C 2.0 or something, right?
C 2.0, that'd be great. Yeah, but until someone figures that out, these bookends of single systems that are over provisioned, or this idealized state of pools of resources, there is a middle ground, right? Which is building, I'll call them islands that are made of themselves of pools, and then doing some, driving some smarts into schedulers that they can bring workloads together so that in aggregate they have smoother usage. So I think that's where the real opportunity seems to be.
I'm going to remind our audience quickly that you can interact with our panelists in the chat and certainly submit a question through Q&A. We are going to come back and get those at the end of this panel. But here's where I really do want to double click on this L word that's come up a couple of times with latency. As we get these larger systems, we started out talking a lot about bandwidth, but latency can be just as important, particularly when you get data dependency on far-flung nodes, or if you're trying to do any kind of coherency between nodes. So I'm interested in what the panel thinks about the importance of bandwidth versus latency here, and if there are any trade-offs. Martin, I saw you just came off mute, so I'll go to you first, and then I'll ask Ivy if she's got anything to say, because she's been quiet for a bit.
Yeah, I'll keep it short. I wanted to react to something that Bill said, right? Because there's two models by which you can do resource pooling, right? You bring the workloads to the optimized resources, right? Or you bring the resources to the workloads, right? And I think we've always sort of been into one camp or the other. And I think we're trying to figure out how do we do both, right? How can you place it in a good place to start with, and then be even better in delivering those what we've been calling hardware resources to it in a better way. Latency is tremendously important, right? Like I said, there is this thing called speed of light, and there's in traditional switching technology, and even if we start optimizing this, right, there are hundreds of nanoseconds worth of delays every time you need to go make an active decision, right, to go left or right, right? It's just the most basic sense. So part of, I think, what we need to do here is find ways where, yes, optical transport, speed of light, right, that's our limit, or speed of light within a fiber anyways. But then how can you eliminate switching off, right? How can you orchestrate end-to-end connectivity between a resource and the consumer of that resource, right? That doesn't require active decisions for every packet or whatever definition of piece of information that you want to transfer. And I think that's, we should not underestimate the control plane required, right? To actually drive that down and create that end-to-end connectivity on demand at a really fine granularity.
As the different classes of algorithms, some of them just inherently latency bound, and my view is are we finding one solution for all, which I think actually we're trying to map different classes of workloads to suitable resources. So what I see is we're providing heterogeneous pools of resources that's on one infrastructure, and we map and their needs, which is in latency or in capacity or in bandwidth, to the different pool of resources they could provide. So to that end, maybe a better way to look at this, how we actually could express the standardized way of describing the resource, the application specific standard of what's the latency, was the quality, was the limits they actually demand to have. Could we not compromise, but kind of make the handshaking possible by meeting in applications a limit on the quality versus what all the heterogeneous pools we have on the infrastructure. It may not be the most ideal or optimal solution, but that's what I see, how, because we're not building one system for all, right? So it's something to have a overall system throughput. That's maybe the ultimate goal.
Yeah, maybe I can just chime in a little bit, since speed of light was mentioned a lot of times here. It's 5 nanoseconds per meter and in fiber. And what's interesting about that is, as Bill was mentioning as well, you can kind of draw a circle for depending on the application. And let's say if the memory access is your goal, to have like a certain small fraction of the memory access latency be kind of dedicated to this overhead, and kind of draw a circle how many racks you can actually reach within that margin. But the interesting thing is you still get at least 2 orders of magnitude of scaling compared to a single chassis in terms of what you can reach in that let's say single memory access without overhead. Now, there are a lot of ways to exploit this abundance of optical bandwidth for over provisioning and fan out. So you can, within that island, create glueless type of architectures, or add some, there are examples of SoCs that have some smart switching and routing embedded in them, so you can create interesting networks like HyperX and things like that. But I definitely also agree with Martin that, another big item is the protocol latency. And even in a glueless fabric, the protocol is really the key. And Slingshot is one of the great examples how, a smart design of a protocol can bypass some of these latency issues. And I think a lot more innovation needs, as we are unlocking more and more bandwidth. It's basically a simple queuing theory rule that basically tells you the more bandwidth you have, the latency becomes way more critical for the digital design. And this is something where I think a lot, as these new high bandwidth solutions are emerging, a lot more work needs to be done on the actually fabric protocol to be able to actually pump that much data in and retain all the ACKs and NACKs and everything that flows in at the right rate. So.
Bill and Mohammed, you've both been waiting on this one.
Yeah, when I think about latencies in a memory application, it really is application dependent. And in today's studies that we're exploring, right, the impact of latency of near memory and far memory on specific performance aspects of those applications. But the biggest wall, as you want to look at it, is when you start stalling the CPU, right? If the CPU is stalled, from bandwidth perspective or from a latency perspective, that's when you really have an issue, because now all the scaling you've done in the last 12 years or so on the CPU speed becomes a big dip for a period of time, and it takes a lot of cycles to recover from a stall. So
oh yeah, you have a memory miss or a memory fault of some kind in these larger systems. What's the failure domain of that, or how do you handle a failure gracefully? Bill, I've heard you use the term blast radius of a failure. That's something we could do a whole separate half hour or hour on. I doubt we're going to have that much time to get into it, though.
So the bottom line is, fault tolerance is another area that becomes of criticality, and reliable connectivity to the solutions, to the pools of composable disaggregated solutions become more critical in a system that's all interdependent, right? So if you have dependencies on pools of composable devices, they all become necessary to become very fault tolerant and capable of resilient operations and supporting those capabilities within that short period of latency. So again, the challenge is, as we talked about the 5 nanosecond per meter, but it's also the layer of logic that comes in between that has to make the decision that the interface, the emerging memory interface protocols add latency, the switching latency, if there's a switching fabric somewhere that has to make a decision of you going which direction. So a lot of these stacks require us to have tiers of memory infrastructures, and interconnecting those and providing the layers of software for orchestration between them become the biggest task ahead of us.
All right. Well, so Bill, I'll come to you in a second, but that's really a good setup for what's really a wrap-up question here. And we'll go back in reverse order from how we did the first question. But we've heard a lot about optical interconnects as a potential solution, and composable disaggregated architectures. Bill, when you look at high performance computing and start thinking about the potential, what kind of opportunities get opened up if the system components have better or equal access to high bandwidth memory and other components at scale?
Well, I talked about this before, which is, there's this ideal of being able to have just, a knob for the amount of memory, a knob for the amount of bandwidth, storage, accelerators, and so on, even different types of compute accelerators and so on. The challenge, of course, is that we know that at least a subset of the workloads in high performance computing are the most sensitive to the latency, to the bandwidth, and so on. And as Mohammed just touched on, the moment you starve the CPU, it's a very big penalty. So I think the first thing is getting past the limitations of copper. That's it. We pretty much understand that every time we bump up the speeds of the SerDes, the wires get shorter and shorter, and so we're constraining our ability to compose and mix and match resources. So optical seems like a clear path long term. After that, I think Martin, touched on this, which is, beyond the speed of light, there's the control plane. There's all these things that are chipping away. So as I start to open up possibilities for composability at the same time, I'm starting to exclude workloads. So I think we're going to find as an industry, it's a pretty delicate balance of finding that sweet spot. But I think the point that Vlad made, which is there is a definable radius where you can bring advantage, considering the speed of the control plane and the speed of light, and get you into the right ratios. And so I think there's a lot of interesting things that are going to happen where we open up some composability, maybe at the rack level or row of racks level in the near future.
Okay, so I said I was going to go reverse order, but Martin, Bill was kind of setting you up there. Do you want to go next in terms of what opportunities get opened up here?
Yeah, it's perfect, right? I mean, and I think we talked about most of it, right? The ability to create systems, right, that are ultimately more flexible, right, that are better for utilization. This is an economics question that we're trying to solve. It's like, how do we get better utilization? How do we get less stranded resources of any kind? Memory here, but you pick it, and it costs if it's not doing anything. And so the challenge is really, the opportunity is, how do we make these systems? The challenge is, right, how do we not just look at the physics, because we have a tendency to try and solve physics problems. But we need to realize that this is back to the composability, that this is a software challenge as well that needs to be overcome. But with these advances that are being made around silicon photonics and around the integration of optics into our chipsets and the packaging and everything else, it puts a new emphasis on what capabilities do we now need to drive into the control planes to actually make use of those in a level of granularity. And if you can think about, right, doing composability at not just a workload level, right, but actually specific pieces of jobs within workloads, right? We've talked about, inside of a workload, you have completely different patterns depending on where you are in the execution of a workload. If you can actually, react to resource needs at those kind of granularities, the opportunities are tremendous, right? Whether it's in the cloud, whether it's private, or whether it's even in between for some of the things that allow that kind of resource pooling. And I think that will, right, create a new level of system, a new level of architecture and resource utilization that we have not seen before.
All right, Mohammed, back to you, the opportunities.
The opportunities from my perspective is how to solve the problem in the most efficient way possible at the level of TCO for a system, for a cloud system that can be serving not the highest level of criticality where for HPC, but at least find the sweet spot and find the area where you can actually serve the majority of the applications in HPC at a reasonable cost. And I think, commoditizing some of those solutions and making them closer to the procurement teams to be able to accept. I think that really is the biggest next step is, and how do we, as a provider of commodity solutions in the past, how do we move forward and help in this in the next phase of evolution of memory composability?
Vladimir, you're right in the middle of this transition to optical. What do you think?
I think it's really several points. One at the architectural level, as people have been saying on the panel, it's really like democratizing access of the SoCs or XPUs to the memory. On one end, you have GPUs who now, even within a chassis, would rather talk to each other's HBM than to a relatively large DDR memory on the node, simply because of the large access latency or how the system is set up. On the other hand, you have examples like Fugaki, where if you were bringing HBM to kind of the CPUs, they would also do better, right? And even on AI workloads. And so I think being able to free yourself as an architect to have the desirable amount of memory and bandwidth at a reasonable latency, regardless of whether you are programming a GPU or a CPU workload in the system, I think is one of the key things. And optical I/O brings that benefit because it lets you connect these components at sufficient bandwidth and fan out. I think, as Mohammed said, one of the key things there is, though, setting up the ecosystem on the physical side so that you have the right system vendors, the right packaging ecosystem, the right chassis platform design, so that you can scale all this up. And in Ayar, we've been trying to stand up that ecosystem. For example, the CWM MSA around laser modules, and working with the OSATs on packaging and even chassis and platform designs. But I think this is where the TCO things for system integrators are going to come in. How rich is this ecosystem to support these new platforms?
And Ivy, I saved you for last on purpose before we go to the audience Q&A, because you're at the National Laboratory, right? And it's in your charter to push the boundaries of scalability and capability for high performance computing, supercomputing, AI. What do you see as the opportunities presented by system components having better access to resources and memory?
So I consider there are several opportunities. Mainly, I will speak from two perspectives. The first one is the system level, right? So now we have system components moving from traditional peripheral devices to have such like equal access to high bandwidth memory that will be able to enable new system architecture for both specific and also varied HPC, AI, and data science workloads. That's the flexibility it could enable for the system level architecture, and could enable more economic way to build a system or even upgrading as a component. So the second perspective I would talk is like from the workload application perspective, right? If we could configure or provide the resources to better suit the what workload or one application need in a more flexible way versus what today they have kind of to request based on some like peak resource usage. That for individual application, they could see a performance improvement, and overall, we might be able to see at the system aggregated throughput, we will see a weighing how the amount of workloads and the efficiency on the system could be improved. So yeah, so I think that there are great opportunities there.
I think those are fantastic perspectives that can completely change how we even use the word peripheral and how we think about hooking resources into the system. And I could keep talking to the five of you for a long time, but I'm very interested in getting to the audience Q&A. So I'll thank my panelists here, Mohammed Al-Battal, Ivy Peng, Vladimir Stoyanovich, Bill Magro, Martin Terpstra, and this isn't quite goodbye yet because we're transitioning over to the live audience Q&A. So let's get started with that. Thanks very much. Hi, everybody. Thanks for being here for this webinar. And due to the magic of Zoom webinars, I have shaved, gotten a haircut, put on a different sweater, and I'm ready for the live audience Q&A here together with the panelists. We've had a lot of great interaction in the chat and Q&A function, some of which have been answered live as we go, but I'm really interested in following up on some of these questions. We don't have a lot of time, but I do want to dive in. One of the interesting things here is someone's setting it up by saying, given the cost of DDR4/5 memory, and the cost of on-package optics, how much does the cost of optics have to change to really make this be a practical solution going forward?
Yeah, so maybe I can chime in first, since the optics has been mentioned. This is exactly the type of problem that the optical I/O is trying to solve, and in two ways. One is that the optical I/O allows us to pool the memory resources. And instead of over provisioning the memory per node and have it stranded or being private, as Ivy has shown, there's a huge fluctuation of the workload requirements. The optical I/O allows you to pool the memory resources. So if you look at kind of the number of nodes in the system, the memory savings can be very significant. And those memory savings can partially be reinvested in re-enabling this optical I/O infrastructure. And so we see that as a very cost-effective way to essentially design the whole system. The second is that optical I/O is kind of the most integrated version of these types of interconnects, where you have all the optical function in a single chiplet in the Ayar Labs solution. So that level of integration allows you to have significant cost savings in deploying these types of systems. Very similar story on the types of laser modules we're built, where you can power many wavelengths from a single module, amortizing the cost further, and ultimately driving the solution to be a fraction of the cost of the units it connects to, which is the goal for a very efficient fabric.
I'm going to let other people comment on that, but also simultaneously up-level the question with incorporating something else that's in the chat. You know, we've been talking about optical interconnects for over a decade. I remember covering that in a blog, I think 12 years ago after an SC conference. So it's definitely been part of the conversation. What's new in optical interconnects that's making it more topical now? Combine that with the cost question.
So I'll happily take a minute or so of that. So yes, we've been talking about optical interconnects, not just in HPC, but in many other places as well, right? But for any of these technologies to become a reality, right, you need two things. You need technology to advance far enough where it becomes practical to use it. And then most importantly, you need to have an economic need, right? You need to have a need to drive a change. And I think we're sort of finally at that point, right? From a need perspective, we're reaching the limits of what we can do signaling wise through copper. Right, so we're actually reaching a piece of physics that is, it may not be a hard wall, but it's going to drive the cost up of doing, higher speed, faster interconnects using traditional technology. At the same time, optics development has sort of gotten to the point where within a few years, integrated optics become economically viable, right? To sort of get that balancing point of where does copper become either impossible or so expensive, and integrated optics becomes viable enough to go and do that. So I think that's a primary driver, and I think that's why this is going to be different than a good idea 10 years ago, right? There is actually economics and physics needs to actually go and drive and get there.
Mohammed, Bill, Ivy, did one of you want to jump in on that?
Yeah, I think the point made about the necessity is really driving the innovation right now, not only on the silicon photonics side, but also on low cost optics and advanced VCSEL solutions that could help us keep the overall cost down in that aspect, and keeping in mind that the reach level is not necessarily kilometers in this case. We're talking about rack level disaggregation of memory. So hopefully we'll be able to solve these problems in an economical way. And as we adopt these technologies further, the economy of scale will prevail, and hopefully the solutions will become more affordable and bring a better TCO to the overall equation.
Ivy, I'm particularly interested in your perspective on this next question. We're talking about heterogeneous architectures and also the differentiation in workloads. And somebody asked, is it really practical to be talking about any type of system that's really good at managing all of these types of workloads? And I'm kind of putting my own editorial spin on it. Is that practical or is that fantasy? You're in a position where you've got to handle all these types of workloads. How practical is that?
So I think, the diversity in workloads, as we show in the previous slides, definitely drive the need to have more different resources. But also, if you're looking at the workloads, providing the memory or improve the memory resource provision to address their performance bottleneck, that would definitely bring improvement. But also keep in mind what we see from previous experience is that when we increase the memory capacity or bandwidth, then the performance bottleneck, they might eventually change. We see that the shift or transform in workloads from memory bandwidth bound to compute bound when moving on a new system with higher memory bandwidth. So eventually, the workload, the performance is something achieved through a balance of memory and compute and extra other stuff. So definitely having a system that with more heterogeneous resources that would improve the flexibility to cope with workloads needs. But if it, but keep in mind that it's a very kind of a whole package, not just one aspect. So we need to keep in mind that when focusing on one aspect of the system, we still need to look at the whole impact to the workload.
Bill, you probably have a perspective on that as well from the cloud standpoint of serving up different types of workloads.
Yeah, I think I do. I'm, my background is high performance computing, so I'm not really, someone who delivers cloud technologies per se, but ultimately this comes down to resource management, right? And if we look at the schedulers we're all familiar with from the high performance computing world, they are dealing with a fixed set of resources by and large, and matching workloads, right? And implementing policy. And if we get to a world where we can actually compose things, then schedulers have to start thinking about what can I create, and I'm dealing with the constraints, whether they be performance, cost, licensing, physical location. Obviously, there's a lot of sophistication that exists in cloud schedulers today to manage the diversity of resources. But I do think it's very feasible. There's a lot of new work there, but it is feasible once we've got configurable infrastructure and the APIs to compose, on the fly.
One last quick question then around the table. Someone's asking about the readiness of the system integration ecosystem around some of these innovations. I'll address that from the standpoint of gap analysis. What else needs to be developed in order to make this a reality? Are we looking at software or interfaces, packaging, rack designs? What needs to be developed in order to bring all this to fruition?
Yeah, we've seen the interfaces change dramatically, and protocols that are specifically created to address the coherent infrastructure that's going to be needed in the evolution of memory disaggregation and pooling. I think fabrics is the next thing to be developed around those interfaces for emerging memory to be possible in a disaggregated solution. So, I think the ecosystem will, at least, is heading in the right direction due to necessity, as Martin stated, and it's feasible within this decade, I believe. But it's going to be a lot of investments from many contributors and collaboration and in a very open and collaborative standards-based solutions.
Martin, Vladimir, do you agree on that?
Yeah, totally. Real shortly, there's a lot of work left to be done, right? I think there's a lot of good direction. There's good momentum. There's incentives to go there, right? And I think that will drive it. Right? But from a technology itself, but then also think about how do you do packaging, how do you do reliability, right? You're changing the way a system is built. You're changing the way a fabric is built from something that we've been doing for about 10, 15 years. So you gotta look at some of those things that we built into the system over and above the technology, and see how do they apply in this new kind of model. But we're a few years away, but I think we're on a fast track, right, to get some of the initial systems together in the next few years.
Vlad, top of the hour, last word's yours.
Yes, and I agree with that. What you'll see is kind of a mix of proprietary solutions and standardized. And as proprietary solutions are kind of easier to develop first and adopt in interesting new architecture systems. In Ayar Labs, we're working on both, and we're also trying to enable the manufacturing ecosystem. An example is CWWDM MSA for laser modules and laser grid, as well as trying to figure out how to use solutions like CXL or other protocols that are anticipating optics in a sense, or memory semantic fabrics, to be able to accelerate the adoption with the optical I/O.
Well, that's unfortunately all the time we have remaining for this live Q&A. I think this could go on for a long time with a very interesting topic. And I'd like to thank all of our panelists and attendees again. I've really enjoyed this discussion. I hope everyone else has found it valuable. All attendees are going to receive an email containing a link to the webinar recording so you can watch it again, share it with someone else who might be interested. If some other question comes up, there should be some engagement available afterwards. If you're interested in more information on Ayar Labs or optical I/O technology, please visit the Ayar Labs website at www.ayarlabs.com. Thank you for your time and attention today, and I'm looking forward to seeing you again soon. Thanks, panelists.
Thank you.
Thank you all.
Thank you.